Good morning, everyone. Hope you're all doing well. Hope the third test went okay. I think it's a little more challenging than the other two were, but it's done now. And we're moving into the last section of the class. So we really only have 2 weeks, like less than 2 weeks. You will be taking your final exam no later than Friday of next week. So we've got 3 sections or 3 chapters left. The next one is all on gas laws. So gases are very unique in that they occupy a large amount of space. The particles don't really interact with each other. And because they don't interact with each other, they have very sort of consistent properties and relationships like volume and temperature, amount, all these things relate very regimented to each other. It's not something that we would see with solids or with liquids. So none of the equations and stuff that we're using for this will apply to the other phases. We will only be using this for gases. So they start off here with extra long straws. I don't know if anyone's ever done that, like at the movie theater when you were a kid and you took like a bunch of straws and chained them together and figured out how long, you could make your straw to drink your pop. Well, there is actually, even if you were the perfect straw sucker, there is a certain length to the straw where you can't make it any longer. And that length is about 34 feet or 10.3 meters. That would be if it was attached to like a vacuum. So it was a perfect seal, perfect suck. Why can the straw only be that long? Why can't it be longer than that? What's going on? Well, let's talk about some things that go along with gases. So we have this idea of pressure from a gas, and pressure is the force exerted per unit area by gas molecules as they collide with the surface around them, because gases have a lot of energy. So they're sort of like ping, 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 ping all over the place. And every time they ping against something, whether it's the wall or your skin or the surface of a liquid, they are exerting a force. That overall force from that specific gas is the pressure that it exerts. On Earth at sea level, the gas molecules in our atmosphere exert an average pressure of 101,325 newtons per meter squared. If you've taken physics before, a newton is a unit for force. Meter squared is an area. Remember, pressure here is force over area. We don't use this quite too often as a unit, but that is what we have. In the English units, it's 14.7 pounds per square inch, or you guys heard of a PSI? Like when you're filling up a bike tire or a soccer ball or something, you have a certain PSI, pounds per square inch. So as far as what's happening when you use a straw, this straw is open to the atmosphere. So the pressure that the gas in the surrounding atmosphere is exerting on this liquid is equal outside the straw as it is inside the straw, right? So all the little force arrows are pointing down and they're equal. Well, when you put a seal around the straw and you start to suck, what are you doing? You are dragging air out of the straw, which is lowering that little vector arrow, right? So these arrows are still staying pretty large. This arrow is getting smaller. So what happens now is the fluid that you have in the cup is going to rush into the straw. So you're not actually sucking the liquid, you're sucking the air up to create a vacuum, which then pulls the liquid up. If we had, again, our perfect straw attached to a perfect vacuum, well, there's only so much pressure that's being exerted by the atmosphere around it, right? So if we had a perfect vacuum and we sucked this as hard as we could, the orange liquid will only be able to rise to 10.3 meters. because again, the vector arrow on the outside, the pushing on the outside is only so large. If we were on, if we were in some place like, trying to think, Venus that has a lot more gas, a much thicker atmosphere, we'd probably have a higher pressure here and we could get that higher, okay? But just for our atmospheric purposes, 10.3 meters is the highest it's gonna get. All right, enough with straws. So let's go to the kinetic molecular theory, which is a model for gases. And it's a model to understand the behavior of gases, why gases do sort of certain things kind of uniformly. It predicts the correct behavior for most gases under most conditions. But like all models out there, the kinetic molecular theory isn't perfect and it does break down under certain conditions. Now, for the sake of this class, we will stay within the paradigm of the conditions that work, okay? So these rules will apply to all the gases that you know. Times that these don't work, the kinetic molecular theory, anytime we have really high pressure or really cold temperatures, anytime the gas particles get super close to each other, they kind of start to stick together and some of these things fall apart. So here are 4 postulates that go along with the kinetic molecular theory. The first one is that a gas is a collection of particles that are in constant motion. So they are always moving. They are active buggers. And not only are they in constant motion, they're in constant straight line motion. So they're not like corkscrewing around or taking sort of a meandering path. They take a very linear path. Now, as these particles, whether they're atoms or molecules, as they're moving through space, at some point, you know, even though it's a huge vacuum, a lot of open space in between them, at some point they're going to collide into another particle. And when it collides, there is no attraction or repulsion between the particles, okay? So like right here, we've got these 2 guys hitting into each other. They're not going to stick together. They're not going to push each other away. They're going to act sort of like billiard balls in a collision. So they're going to perfectly hit each other and ping back off of each other. So this is why gases won't like clump together in a corner, okay? Gases, and we've already talked about this, have a lot of space between the particles compared to the size of the particles themselves. So good amount of empty space. And then number 4, the speed of the particles. So how fast these little billiard balls are going will increase with increasing temperature. So if I put more thermal energy into the system, these guys will speed up. This is saying the exact same thing, but gases move in straight line paths. They don't attract or repel each other. There's a lot of space between the gas particles compared to the size of the particles themselves. And the average kinetic energy, or the energy of motion of the gas particles, is directly proportional to the temperature of the gas in Kelvin. We're going to be using kelvins for temperature with gases. This means that as the temperature increases, the particles will move faster and therefore have more energy. So a very, very hot gas, a gas at 400 degrees C or 400 degrees K, will burn you much worse than something at 200 degrees K. So this is consistent. This model is consistent with all the things we know about gases already, right? Gases are compressible because we have a lot of empty space. Gases assume the shape and volume of their container because the particles don't clump together. They don't interact with each other. So if they've got space to spread out, they're going to spread out. They're going to disperse. Gases have low densities in comparisons to liquids and solids because they are a lot of empty space. We've seen this image before. Here's our gas. Look, compressible. Liquids, not so much. Solids, not so much. So a gas assumes its container. including the shape and the volume. Since the attraction between the molecules and the gas are negligible, the particles are in constant motion. They will just expand forever to fill their container. As far as the density is concerned, if I was to take 1 can of liquid pop and convert it into a gas, it would be equivalent to 1,700 cans of pop. Okay? So the gaseous counterpart to this can of pop is quite large. So pressure, which we've already talked about with the straws, but pressure is the result of the constant collision between atoms or molecules in a gas and the surface around them. Because of pressure, we can drink from straws, we can inflate basketballs, and we can move air in and out of our lungs. So when we inflate, for instance, a basketball, the pressure inside the basketball is greater than the pressure outside the basketball. That's why it expands out. Variations in pressure in Earth's atmosphere are what allow there to be wind, and they allow us to predict weather. All right. Let's see, this is talking about being in an airplane. Again, this stuff isn't like super important, but you guys have experienced changes in pressure every time you go up in an airplane. So when you're on the runway, the pressure inside your body and the pressure outside your body are equal to each other. So you don't notice anything. When you go up in the airplane, the pressure outside your ear decreases pretty quickly, but the pressure inside your body still stays relatively consistent to what it was on land. So your eardrum will actually sort of bevel out, and you'll feel that, right? It feels kind of like icky in your ear. And so what do? You chew gum, you try and blow your nose, you try and quote unquote pop your ears. And what you're doing is not actually popping your ears, but you're trying to release some of the built up pressure within your sinuses so that you can come back to an equal pressure so your ear doesn't feel icky, right? Same thing happens when you go down on an airplane. When you go down, the pressure inside your body is lighter because it's used to the higher altitude. The pressure outside has increased, so your eardrum will actually sort of bevel in. And again, you do the same thing. You chew gum, you pop your ears, you do whatever to try and equalize the pressure in your sinuses. So pressure equals force over area. We're not going to be doing any calculations with this, but just know that it's a force over area. More collisions you have, the more force you have, the more pressure you have, right? Or the smaller area with the same amount of force, the higher pressure. So look at these two canisters. Which one would we expect to have a higher pressure? The lower one, because it has more particles to hit the surface. Same area, right? Same volume to the container, same area of glass, but this has more particles to create more collisions, so increased pressure. Some of the units of pressure, the simplest one, the one that we use a lot, is the atmosphere, or the ATM. At sea level, it's 1 ATM. Okay, so here in Asheville, we're just slightly less than 1 ATM, not anything substantial, but we're just a hair less than 1 ATM. The SI unit for pressure is the Pascal, which is defined as 1 Newton per meter squared. And we already went over this, but 1 ATM is equal to 101,325 pascals. There's some other units that we use. Millimeters of mercury. Have you guys heard of millimeters of mercury before? If you ever look at like the weather systems and say, low pressure system, 450 mmHgs. What is that coming from? Well, when you are at 1 atmosphere or at sea level, if you have that setup where you have the perfect vacuum with mercury as your liquid, the atmosphere outside will push down and it will draw the mercury up. Specifically, it will draw it up 760 mm's. So 1 atmosphere is equivalent to 760 mmHgs because that's the height, millimeters of mercury. At sea level, it will, in a pure vacuum, mercury will rise 760 millimeters or 76 centimeters or 0.76 meters. There's another unit here called a torr. A millimeter of mercury and a torr are the same thing. Okay, so it's a 1-to-1. And we've got some other guys down here. Inches of mercury, I don't really use that one a whole lot. This one we see though sometimes 1 ATM is equal to 14.7 PSIs. So pounds per square inch. You know, like when you're, like I filled up my bike tire the other day and it wanted 60 PSI. So, you know, it wanted roughly 4 times as much as what the atmosphere is. So my bike tire is pushing out in the atmosphere 4 times as much as the atmosphere is pushing in on it. So here are all the units. And we can convert with these, right? Awesome. Okay, so real quick, I'm going to give you a unit conversion, give you like 2 minutes for it. Given that you have 892 millimeters of mercury, find ATMs. I'll give you a minute and a half. All right, so from what we know, the relationship between millimeters and of mercury and ATM, 1 ATM is equivalent to 760 mmHgs. So we start with the 892 millimeters of mercury. We're going to put the 760 on the bottom because we want to get rid of that, right? We want that to go away, and that's for every 1 ATM. So we really are just taking the 892 and dividing it by 760. We get 1.17 ATM, so just slightly more than sea level pressure. Okay. The calculations that are in this chapter for gas laws are not that complicated. They're just really not, it's a lot of just plugging and chugging. So you always want to make sure that you're matching your units up because that's where they will trip you up a little bit. They may give you an equation where it's in millimeters of mercury and you really need to have it in ATM in order to finish the calculation. All right, so why airplane cabins are pressurized. So because you fly so high above 25,000 feet, the pressure is below 0.5 ATM, which means that you're just not experiencing the same levels of oxygen as you would at sea level. So lower levels of oxygen can cause dizziness, headache, shortness of breath, unconsciousness. So commercial airlines have to pressurize their cabins in order for you to not pass out. So we're going to talk Boyle's Law. All right, there's a bunch of laws. I don't really care if you know the names of them and stuff like that, but you do need to understand their relationships. So the pressure of a gas sample depends in part on its volume. If the temperature and the amount of gas are constant, the pressure of a gas sample increases for a decrease in volume and decreases for an increase in volume, or they're inversely proportional. So I'm going to write this on our slides over here in a little more useful way. So Boyle's Law, we're going to keep temperature and amount. I'm going to use N, little n, that's for moles. Okay, moles. So if temperature and amount are constant, then we find that pressure is inversely related to volume. Okay, as one goes up, the other goes down. What is the actual equation for Boyle's Law? It says P1 V1 equals P2 V2. Now the ones are referring to your initial parameters. The twos are talking about your final. So you want to make sure that you're pairing things up in such a way that like the variables that are your starting point go in the initial slot. Your variables in the final go in the final slot. How many variables do we have here? 1, 2, 3, and 4. 4 variables, so you'd be given 3 of the 4. A real life example of this inverse relationship is a bike pump. So when the bike pump is, when the plunger is all the way up, you have a large volume, right? And you have relatively low pressure. It's easy to push the plunger down in the beginning. But as you get towards the bottom, it's much harder to push the plunger down. Why? Because you have a smaller volume, which means you have a larger pressure. So taking a certain amount of gas and squeezing it into a smaller space will increase the pressure. We do this all the time when we have compressed gas. It's a gas that's been moved into a smaller container. So volume is inversely proportional to pressure. Okay, we can move through some of this. Really just overkill here on all of it. Okay, so let's look at this one. A cylinder equipped with a movable piston has an applied pressure of 4 atms and a volume of 6 liters. Those are your initials, right? That's where we're starting. So this here is P1. This here is V1. What is the volume of the cylinder if the applied pressure is decreased to 1 atm? All right, so this is my new pressure or my final pressure, that's P2. Volume, V2, is what we want to solve for, right? So gives you 3 of the 4 variables. So as far as solving it, you just line up your variables, make sure you're labeling them correctly. Always check that the units are the same so that if it's starting with ATM, you're ending with ATM, right? We don't want this to be an ATM and this to be in millimeters of mercury. That wouldn't translate well. We're trying to find the second volume. So we use our equation. There's our equation, P1 V1 equals P2 V2. We're going to isolate for V2, right? We're trying to find the final volume. Some people like to plug all the information in and then switch it around. You can do that. Or you can say, I'm going to solve for V2. which means I need to get P2 over to the other side, which is what's happening here. Plug all your units in, or all your values in with the units, because what will happen is the units will cancel that are no longer needed, and the unit that is left behind will be confirmation that you are finding a volume, okay? So we take the 6 liters times the 4 ATMs and divide it by 1 ATMs to give us 24 liters. Does that feel kind of refreshing after the last chapter? I mean, it's not too tricky. I'm gonna have you do one Boyle's Law problem, but we're not gonna, I mean, I'm not gonna insult your intelligence, okay? Like these problems really aren't that tough. So what is the initial pressure of 40 liters of gas that compresses to 18 liters and has a pressure of 3.6 ATMs. Okay, so what is the initial pressure of 40 liters of gas that compressed to 18 liters and has a pressure of 3.6 ATMs? I'll give you guys 3 minutes for that. Okay, so I'm not expecting you to know, oh, I need to use Boyle's law here, but you do need to see that you have a problem. There are some initial parameters, there's some final parameters, and the initial and final parameters are talking explicitly about pressure and volume. It doesn't mention anything about temperature or amount. So I know that I want to use hello. P1 V1 equals P2 V2. Now, what do I have? Well, it says it wants to know what the initial pressure is. We know what the initial volume is. It's 40 liters. I know that it's compressed down to, so I know the final volume is 18 liters, and I know the final pressure is 3.6 ATMs. So I'm just going to plug it in. I want P1. So P1 is going to equal P2 V2 over V1. It's important to make sure the 2's and the 1's stay with the right spots, okay? It's easy sometimes for people to flip those around or, mismatch a 1 and a 2. Don't do that. All right, so 3.6 ATMs times my 18 liters all over 40 liters. We'll see that the liter unit will cancel. We get an initial pressure of 1.6 ATMs. You can always say, does this make sense? Well, yeah, I was at a bigger volume, so I would expect a lower pressure, right? As we decrease the volume, we increase the pressure. So that looks good to me. Let's move on to the next law. All right, so why do hot air balloons rise? Blah, 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 blah. Okay, so the next law that we're talking about is Charles' law, which is going to relate volume and temperature, right? So in this one, we're going to keep pressure constant and we're going to keep amount constant. So we're not going to change those. As we increase the volume, the temperature will increase, or if the temperature decreases, the volume decreases. They are directly related to each other. Here's a drawing of a generic gas. And what you'll see is that as the volume is on the X, temperature is, or rather volume is on the Y and temperature is on the X. As we increase our temperature, we increase our volume, right? A hotter gas takes up more space. Now, what happens if we were to take that gas and cool it all the way down? It would take up less volume, right? What if we kept cooling it all the way down? Well, at some point, we're going to cool that gas so much that its volume gets to pretty much 0. And that is absolute Kelvin, or absolute 0, which is 0 degrees Kelvin. Okay. We can't get colder than this, right? We say in the universe, -273 Celsius or 0 degrees Kelvin is the coldest temperature. Can't get colder than that because if we were to get colder than that, the volume of the gas would start to become negative. You can't have a negative volume for a gas. That's the cutoff there. That's when all particles cease to move. There's no more motion left in them. Because of this, we don't like negative numbers in these calculations, so we will always want to convert into Kelvin. All right, so when you're using Charles' law, your volume can be in whatever unit as long as it's the same on both sides, but your temperature has to be in Kelvin. Let's see some other examples of this. If we have a balloon filled with air, and if I was to put that balloon, let's say it's made out of a material that can handle large temperature changes. If I was to take that balloon and stick it in ice water, the balloon would look like it wilted. Why? Because the colder it is, the closer together those gas particles are going to get. They're going to take up a lower volume. If I was to take, that same balloon and put it in boiling water, It's going to heat the gas up. Those particles are going to expand. They're going to take up a larger volume. So here is the equation for Charles' law. V1 over T1 is equal to V2 over T2. And all temperatures have to be in Kelvin. It's non-negotiable. If the problem gives it to you in Celsius and says, I want the final temperature in Celsius, you will need to take your initial Celsius, convert it into Kelvin, then put it in the equation, and then go back and convert it into Celsius. You cannot get Celsius anywhere near this equation. Why? Because the difference between Celsius and Kelvin is an addition-subtraction function, which messes with the multiplication division function. It's not at the same order of operation. Volume, though, can be in different units. It could be in liters or milliliters, as long as they're the same on both sides. So here is a problem. I want you guys to actually work through this one. So a sample of gas has a volume, because it's really just plug and chug like the last one. A sample of gas has a volume of 2.8 liters at an unknown temperature. Okay, so we know the initial volume, 2.8 liters, and we don't know its initial temperature. When the sample is submerged in ice water at 0 degrees Celsius, so we're assuming it's 0 degrees Celsius, its volume decreases to 2.57 liters. What is its initial temperature in both Kelvin and degrees Celsius? So I'll give you guys 5 minutes for that one. So looking at this problem, here are the variables that we know. We've got V1, V2, and T2. This is the one that we definitely want to convert into Kelvin. So how do we convert Celsius to Kelvin? We just add 273. So we've got our equation. Now we're solving for T1. So I think this can sometimes throw people off, but T1 is right here. T1 is right here. So to isolate T1, T1 will equal V1 times T2 over V2. A lot of times what will happen is people will go, oh, okay, I'm going to divide this side by V1. So I'll divide this side by V1, right? And that cancels. But that isn't T1 equaled all this stuff. That's 1 over T1. So then you need to take the inverse of those in order to get it. You need to flip it. So T1 is actually going to be T2 V1 divided by the V2. Okay. So make sure you're being careful with your variable isolation. If it helps to plug the numbers in first, plug the numbers in first and then isolate after. So we've got our 273, we plug it in, we get 0.28 liters times the 273 kelvins divided by the 2.57 liters, and we get 297 Kelvin. Now it says, hey, we want it in Celsius. Okay, so then after the fact, you'll take that, you'll subtract the 273 to get 24 degrees Celsius. Again, don't put Celsius anywhere near the equation. There's another law, it's called the combined gas law. So it takes those previous two and puts them together. P1 V1 over T1 equals P2 V2 over T2. How is this different than the other ones? Well, it has 6 variables, so you'd be given 5 and have to solve for the 6th. Pressure can be in whatever unit as long as it's the same on both sides. Volume can be in whatever unit as long as it's the same on both sides. Temperature, just like the last one, temperature has to be in Kelvin. With this one, we are assuming that the amount of gas is constant, so we're not changing the amount of gas. Okay, so here is a problem that I will have you work through. A sample of gas has an initial volume of 158 milliliters at a pressure of 735 mmHgs and a temperature of 34 degrees Celsius. If the gas is compressed to a volume of 108 milliliters and heated to a temperature of 85 degrees Celsius, what is its final pressure in millimeters of mercury? I'll give you guys a little bit of help as far as organizing the information. Okay, and I'll give you 5 minutes for that. All right. So given 5 pieces of information, need to solve for the 6th. Make sure to convert your temperatures into, temperature 1 should be 307 Kelvin. Temperature 2, final temperature, should be 358 Kelvin. So just adding 273. When looking at this equation, we're trying to solve for the final pressure. We're looking for this thing right here. So we need to move these two guys over to the other side, right? That means we would divide it by the V2 and we'd multiply it by the T2. So those cancel and those cancel. Whatever you do on this side, you have to do on this side. And that's how you know where the variables go. So that is this right here. When plugging it in, we don't have to worry about converting millimeters of mercury. We can keep that. We don't have to worry about changing milliliters because it's a milliliter and a milliliter, so they'll cancel. But we do need to change the temperature into Kelvin, which we did. And we get 1.25 times 10 to the 3 mmHgs, or that's 1250 mmHgs. If the problem had, like, let's say, asked you to solve it in ATMs, you could, after the fact right here, convert, 1 ATM is equal to 760 mmHgs. Let's just do it for fun, because converting is so much fun. 1250 divided by 760, and we get, 1.6 ATMs. That's something that you could solve after the fact, or 1.64 ATMs. Questions on this? These problems are really, they're like, 7th grade math. It's like plug and chug. That's what it is. It's plug and chug. One more law, Avogadro's law. It's the only one that involves a change in the amount of gas. Okay, so it relates volume and moles. The relationship between volume and moles is directly related. So as your volume increases, your moles have to increase, or as your moles increase, your volume increases. Our go-to example of that is this right here. You have a balloon. As you blow more gas into it, what happens to its volume? It gets bigger. So there's a proportionality to that. They're directly related to each other. This relationship was first stated by Avogadro, same dude that came up with the number, Avo's number, 6.022 times 10 to the 23rd. So what is, it doesn't, these slides are so silly. It doesn't even give us the equation. Okay, you probably want the equation, right, in order to solve this. So V1, the initial volume, over N1. Now, N is moles of gas. So remember, temperature had to be in Kelvin. Well, type of gas, or the gas, it has to be in the moles. Okay, you can't put grams in there. So V1 over N1 equals V2 over N2. Looks kind of similar to Charles' law, doesn't it? One over the other on both sides. So looking at a problem for this, it says a 4.8 liter sample of helium gas contains 0.22 moles of helium. This is important. This question is saying how many additional moles of helium gas? How many additional? So how many on top of this should you add to the sample to obtain a volume of 6.4 liters? So first, what I want you to do is just solve for, the initial volume and the initial moles. You have the final volume. First, I want you to solve for final moles. Okay. First, solve for final moles, knowing that V1 over N1 equals V2 over N2. Once you've found final moles, then I want you to find additional moles, and additional moles is going to equal your final moles minus your initial moles, right? Because you've added that much gas. So two-stepper, give you 4 minutes for that, 4 or 5 minutes. Okay, so in this one, the wording is just a little tricky because it says how many additional moles of helium gas should you add? The equation isn't going to give you the additional moles. The equation is just going to give you the final moles. That's why I said first just solve for the final number of moles. So we plug it in. Here's our information. It's already in moles, liters and liters, which is great. We're trying to find N2. So when plugging it in, N2 should equal 0.29 moles. Now that is not the number of moles added. That is your final mole. So you take your final minus your initial and you will get the difference or the addition. So you added 0.07 moles. And so just, you know, for that problem when using Avogadro's, just keep an eye out for that additional moles. I feel like that comes up like in the final maybe, and it comes up like in the homework where it's like not asking you for the final number of moles, but it's asking you for the additional number of moles. So just doing that at last little step. All right, so all the laws we have, everything that we've talked about thus far, if you've noticed, has been a change in parameter, right? So we have initial parameters and final parameters. So we're starting with like a volume and a temperature, and we're ending with a volume and a temperature. There's some sort of change or transformation happening to the gas. Well, we're going to work now on a law that's called the ideal gas law. This is not a change in time, okay, or a change in parameter. This is like sort of frozen in time. So we're not going to say, oh, we have an initial volume and we have a final. We're going to say, hey, we have this volume, this temperature, this pressure. What is the amount? All right. And the ideal gas law is kind of all the other laws smushed together. Sometimes you'll hear it referred to as PV-NERT. PV equals nRT. Real quick, I'm going to pull up here where I've shown you guys in the past where that formula sheet is. If you guys want to use that, print it out and then, you know, add your own notes to it, piggyback off of it. There's a formula sheet and a periodic chart here. But this formula sheet, this would traditionally be what you would be given on a test. You can see it has all that information right here, right? All the different laws kind of combined together. Looking at this, whatever you don't need, whatever is a constant, you just cross it off and use what's left. So like, let's say amount was constant and temperature was constant. What are you left with? Boyle's law. Okay. Let's say pressure stays constant. So we don't need pressure, and amount stays constant. What are you left with? Charles' law. Okay. So that's how you would use that. It's a way that they're all kind of smushed together. Here's PV-NERT. PV equals nRT. Now, let's look at what all those different values need to be. The first one, most important, is R. R is a constant. It's true for all gases. R equals 0.0821, and it has crazy funky units. Liters times ATMs divided by moles times Kelvin. Liters times ATM divided by moles times Kelvin. And if you're like, why does it have these crazy units? Well, let's isolate really quick. So, because why not? All right, so traditionally PV equals nRT. I'm gonna get R by itself, okay? Which means I have to divide by N and T, divide by N and T. So R is equal to P times V over N times T. Well, what's our unit for pressure? ATM. What's our unit for volume? Liter. What's our unit for amount? Moles. And what's our unit for temperature? Kelvin. None of those cancel. They all stay preserved with the R value. That make a little more sense why it's got the funky units? If you're using R and these are the units, what does everything else have to match up to? It has to match those units, okay? So pressure must be in atmospheres. Volume must be in liters. Amount of gas must be in moles, and temperature must be in kelvins. So when looking at it, it's like, oh, there's 5 variables, but R is a constant. So we don't really consider that a variable, right? That's never going to change. So we really have 4 variables. We have pressure, volume, amount, and temperature. So you'll be given 3 of the 4 and you have to solve for the 4th. Sometimes the problem gives you R, sometimes it doesn't give you R, and you're left thinking, oh my gosh, I have 5 variables and I only have 3 pieces of information. Well, you got to go back into your pocket and find R. Okay, R is that constant. Again, do you see here, there's no 1, 2s, no little subscripts. This is not an initial and a final. There's no changing happening here. It's just a set experience. So let's look at a problem right here. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atms and a temperature of 315 Kelvin. So first thing, if you were on an exam, would be what do I need to use? Well, outside of it telling you to use the ideal gas law, we would want to use the ideal gas law. Does it talk about initial and final stuff? No. It's talking about like a specific point in time. There's specific parameters. There's stuff about amount. There's stuff about atmospheres, so pressure, and there's stuff about temperature. So I'm feeling like PivNert is the way we want to go here. PV equals nRT. We want to solve for volume. Okay, we don't know what volume is. It says calculate volume. So I want to isolate for volume. So volume is going to equal nRT divided by P, right? Get the P to the other side. So let's see what our information is. N is 0.845 moles, and it's of nitrogen gas, but that doesn't really matter. If it had been in grams, it would be important to know it's nitrogen gas because we need to convert from grams to moles, but we're already in moles, so we're good there. Our pressure is 1.37 atms, and our temperature is 315 Kelvin. So we just plug it in. I'm gonna clear this out and look at the way they plugged it in because my handwriting is gruesome. Okay, so there we had isolated, we have all of our values, and notice they put the units, even the funky units, they put it on there so that you can see how things cancel. Mole cancels with the mole, ATM cancels with the ATM, and Kelvin cancels with the Kelvin, and we are left with just liters. All right, so we plug and chug, and we get 16 liters. Let's, I'm going to give you guys one of those to do. Over here. Okay, what temperature in Celsius is 44 grams of CO2 gas with a pressure of 840 mmHgs and a volume of 13.4 liters? This is going to require you to do some converting, okay? So write out what your R value is, look at what those units are, and make sure everything matches up with those. I will give you guys 6 minutes for this one because you're gonna have to do a couple extra things. This says degrees C. I don't have a quick degree on my on my pad. So I'll just use that asterisk. Okay, so this is a Pivnert problem. PV equals nRT, and we want to solve for temperature. So our pressure is 840 mm. Actually, even before I write that, I'm going to do my R, because my R reminds me what units I need to have. So R is equal to 0.0821 ATM liter mole Kelvin. So back to pressure. Pressure is equal to 840 mmHg. I don't want to be in mmHg, I want to be in ATMs. So 1 ATM for every 760 mmHg. You want to do all that converting before you get it into the equation. Some people will say, well, can I convert my constant to millimeters of mercury? I mean, if you wanted to, but I would just leave that as is and do the other ones individually. Otherwise, you could get yourself into a pickle. 760. And we get just over 1 ATM, so 1.11 ATM. Volume, 13.4 liters, already in liters. How nice is that? And then amount, we have 44 grams of CO2. It does matter that it's CO2 because we want to get it into moles, right? So 1 mole of CO2 is, what is it, 44 grams? 44 grams of CO2, right? So dun, 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 we have 1 mole of CO2. From there, we can now plug it into our equation. I want to solve for temperature. So temperature is going to equal pressure times volume divided by amount times R, or 1.11 ATM times that 13.4 liters all over 1 mole times 0.0821 ATM liter mole Kelvin. Okay. ATMs cancel, liters cancel, moles cancel, and we should just be left with units of Kelvin. So 1.11 times the 13.4 divided by 1, okay, divided by 0.0821. We get a value of 181 Kelvin. Now, it said, hey, give it to me in degrees Celsius, all right? So in order to get it into degrees Celsius, minus 273. And we get a value of negative 91.8 degree C. 81 minus 273. Oh, no. I put an extra decimal, 92. Yeah, just 92. I'm like, where am I getting a decimal? There's no decimal there. Negative 92 degrees Celsius. Okay. Questions on that? On plugging and chugging. It's really most of what this chapter is. There's a little bit left in here. Yeah, let's talk about, there are some situations where these gas laws fall apart. You won't have to do any calculations for these, but you may want to know conceptually, when do these things fall apart? Non-ideal gas conditions, anytime you have a low temperature or a high pressure. Low temperature means it's cold, the particles are coming closer together. High pressure means the particles are coming closer together. As the particles get closer together, you can get this intermolecular interaction, or they'll kind of stick together and they don't follow those rules as nicely. Okay, so there's this rule of partial pressure that says that if you have a mixture of gas, the total pressure of that gas is equal to all the partial pressures added together. So in our atmosphere, air is a mixture of 78% nitrogen, it's 21% oxygen, 0.9% argon, and 0.04% carbon dioxide. There's some other smaller ones. The nitrogen molecules in the air represent 78% of the total pressure. Okay. The oxygen is 21% of the total pressure. And the trace amounts are their small amount of pressure. So we can look at it here. Let's say we've got this gas mixture and it's helium and neon. Let's say the total pressure is 1 atm. If 80% is helium and 20% is neon, then 0.8 atms is the helium and 0.2 atms is the neon, because Dalton's law of partial pressure says that the individuals need to add together to get to the total. It's really just an addition subtraction thing here. Here's Dalton's law of partial pressure. How many individual gases are there? It's really dependent on the mixture. You can have 40 of them. You guys will probably have just 2 or 3. So for 1 atm of air, right, that's going to be nitrogen, oxygen, and argon. It's going to be 0.78 atm is coming from the nitrogen, 0.21 atm is coming from the oxygen, and 0.01 is coming from the argon. When we add those 3 together, we get 1 atm. So I want you to do this problem here. It's really as simple as addition and subtraction. A mixture of helium, neon, and argon has a total pressure of 558 mmHgs. If the partial pressure of helium is 341 mmHgs and the partial pressure of the neon is 112 mmHgs, what is the partial pressure of the argon? I will help you out. Total pressure, P total, needs to equal P of the argon plus P of the neon plus P of the helium. Okay, 2 minutes to solve this. It's just Okay, so for Dalton's law of partial pressure, we know that the total has to equal all the individuals added together. So we've got this here. We know the total, 558. We subtract the other two components out. So we subtract the helium and we subtract the neon, and we'll be left with 105 mmHgs, which is the remaining argon. It's not going to get much more complicated than that for partial pressures. Just, you may be given each of the individual amount and you need to find the total, or you may be given the total in some of the parts and you have to solve for the other part. Okay, there's only one other thing I want to talk about. I'm not going to go over this. We're not doing vapor pressure in this class. You do that in 151, but we won't be doing it. We're not doing gases and chemical reactions. Just note that, like, hey, you could in fact solve for the N value. If you have PV equals nRT, you could solve for the N value. And if you know N, which is number of moles, you could do a stoichiometric relationship and use a balanced equation, but we're not going to do that. Okay. This I do want you to know though. The volume occupied by 1 mole of gas at standard temperature and pressure, and standard temperature and pressure, STP, is 0 degrees Celsius or 273 Kelvin and 1 ATM. Okay. If you are at standard temperature and pressure, it doesn't matter what the gas is. This is a nifty unit conversion. 1 mole of gas will take up 22.4 liters. So it's kind of a shortcut so that you don't have to use Hibner. It doesn't matter if it's neon gas, it doesn't matter if it's CO2, oxygen, whatever, as long as it's a gas and you're at those specific parameters, this relationship applies. So here is 1 mole of helium at STP takes up 22.4 liters. 1 mole of xenon at STP takes up 22.4 liters. So let's do a problem with that. Okay, what is the volume of 19.4 moles of helium at STP? 2 minutes. Okay, so anytime you see STP, just write out 1 mole is equivalent to 22.4 liters. Those two things kind of go hand in hand with this chapter. So if we have 19.4 moles of helium, well, I know that for every 1 mole of helium, it's going to take up 22.4 liters of space. Again, that only applies at STP. You could also plug this into PivNert with the STP standard units of 273 Kelvin and 1 ATM, but this is a little bit faster. So we take the 19.4, multiply it by the 22.4, and we get 435 liters of helium. Let's do one more. Instead of, let's say, what volume does 32.6 grams of xenon gas occupy at STP? Okay, so this one you have to do a little extra. So I'll give you 3 minutes. All right, so this one's a little different in that I give it to you in grams, and we have a relationship with moles, right? So 1 mole of xenon is equivalent to 22.4 liters. I'm in grams though, I gotta get out of grams. But you should, hopefully by now you're starting to realize that like gram and mole are like synonymous with each other. They're interchangeable as long as you know the identity. So 32.6 grams of xenon, if we convert that into moles, well, 1 mole of xenon, it's a heavier atom, we've got 131.293 grams. Okay. Grams will cancel, and I'm just going to keep chaining it together because I know that for every 1 mole of xenon, it'll be 22.4 liters. In that case, the moles will cancel. We end up with 5.56 liters of xenon gas. So that's kind of that STP one is, this little conversion is kind of nifty to have in your back pocket. And that's it. It's chapter 11. We're done. So, yeah, gas laws. If you want more practice with this stuff, here in the slides, let me show you. They're all jumbled together. So it might be good practice if you want to like test on, test which thing you want to use when. Under our worksheets here. There's a whole packet, okay? And it's got like a bunch of different problems, and it has all the answers on the back as well, okay? This is nice as well because it has, right, this is nice as well because it has all the stuff at the beginning, like all the laws kind of compiled together. We didn't go over Guy-Lussac's law, so don't stress about that one. We also are not doing anything with Graham's law. Do you see this here? Anything with effusion, diffusion, we're not doing anything with that. So if you come across a problem that talks about either of those, don't just skip over it. But we did talk about Boyle's, Charles, the combined, Dalton's partial pressure, and the ideal gas law. And also, it's got like a bunch of useful informations for abbreviations, temperature conversions, unit conversions, things. So this may be something you want to use too for your exam. But yeah, a bunch of good problems all throughout here that you can practice. So great job today. Thanks for sticking with me. I wanted to push through so we could get out a little bit early. If you have any general questions, throw them out there. If you have any individual questions, wait around and I'll call you in one at a time.